Let's more precisely describe the algorithm that builds a spanning tree. First, let's review some prior assumptions. A graph is a stack of edges. A spanning tree is a stack of nodes. A node has the following format: value and children. Edges are represented as pairs. Left and right are the values of the nodes that are connected by the edge. We do not need the edge weight. The description of the spanning tree algorithm contains new functions, so let's define the functions first. The findNeighbors function finds adjacent nodes given a graph and a node. Here are the properties that describe the function. Property 1 says that if left is not equal to v and right is not equal to v, then the output of the findNeighbors function, where the input graph is pair left, right, and rest, value is v, and children are result, is equal to the output of the same function, where the graph is rest, value is v, and children are result. Since neither left nor right is equal to v, nothing is added to the children result. Property 2 says that if left is equal to v, then we add right to the result. Property 3 says that if right is equal to v, then left is added to the children. Property 4 says that if the input graph is empty, then the children is equal to result. As we can see, we find the neighbors by cycling through the edges and looking for the value. When the value is found, the other node is pushed to the children stack. We are finished when the graph is empty. Try using the properties above to prove that the output of the findNeighbors function, where the input graph is pair 0, 1, 0, 2, 1, 3, and 1, 4, the value is 0, and children are initially empty, is equal to the stack 2, 1. Next, let's see how we can find the neighbors or children of a specific node in a graph. The node is specified by its backwards index in the tree stack. The backwards index starts at the bottom of the stack, in contrast to the regular index that starts at the top. Here's an example stack with the element indices and the backwards indices. The top element in the stack is London, followed by Paris, Barcelona, and Munich at the bottom. As usual, the stack index starts at the top at 0 and increments by 1 each time. The backwards index also starts at 0, but it starts at the bottom. Then as you move up, it increments by 1. If we know the length of the stack, we can convert the backwards index to the index as follows. Index is equal to the length of stack minus 1 minus the backwards index. For example, the length of the stack above was 4. If the backwards index is 0, then the index is 4 minus 1 minus 0, or 3. As we can see, when the backwards index is 0, the index is 3. The following property tells us how to find the children of the node at some backwards index back I of the spanning tree T. If the length of stack T minus 1 minus back I is equal to I, and the element at index I of stack T is equal to node VCS, then the children of the node at backwards index back I of tree T in graph G is equal to the output of the findNeighbors function, where the input graph is G, value is V, and children are an empty stack. As we can see, we first compute the index from the backwards index, then retrieve the element at that index of T. This element has value V. Then we search G for the neighbors of V. Later, we will see why we use the backwards index rather than the regular index. Try using the properties to prove that the children of the node at backwards index 1 of the following tree in this graph is equal to the stack 6, 4, 0. First, show that the length of the stack minus 1 minus 1 is equal to 0, and the element at index 0 of the stack is node 2. Then we can claim that the children of the node at backwards index 1 of this tree in the following graph is equal to the output of the find neighbors function, where the graph is still the same, value is 2, and children are empty. Then we can show that the output of this function is equal to the stack 6, 4, 0.